This video is about timing in synchronous sequential circuits. The main elements in such circuits are registers to store the state, combinational logic to evaluate some Boolean expression, and the clock signal itself. For this video, we will assume our register elements are rising edge D flip-flops and that the clock signal is ideal, that is, its transitions from low to high and from high to low are instantaneous. In order to build things up conceptually, we will start with simple, small circuits and build our way up. First, I would like to talk about timing diagrams in general. A timing diagram shows how a signal changes as a function of time. For digital logic, this is going to be between zeros and ones. Everything is in binary. So we may have a signal x, and the timing diagram will show that it starts off, for example, at a 0, goes to a 1, then goes back down to 0, then 1 for a little bit, and so on. It can keep on transitioning and we can track what's happening to it through this timing diagram. We can then show another signal y that does something in response to this signal or maybe independently of it. There is another kind of thing we can show in here, and that is indeterminate values. So for example, if we have something that looks like this, where we shade in a particular region, what we're basically saying is that we don't know the value of y in this region. It's not necessarily a 0 or a 1. Of course, the actual value of y is going to be either a 0 or a 1, but the point that we're trying to get across here is that we don't necessarily know what it is, and therefore we can't treat it as a particular value. And so maybe then it goes back to being a concrete 0, and then maybe for a while later it's indeterminate once again for some reason, and then it becomes a nice 1, and then goes down, and so on. Another thing we can show is general validity of a signal. So for example, if we don't really care what the actual value of x or y is, we just want to know that the signal is valid or invalid, we may draw something like this, where we will have just a light box to indicate a valid value, and this kind of a switch over here with this x shows that the value of z changes. And again, it doesn't matter what it changes from or to, only the fact that it's valid. And then we can keep going, and maybe at some point there's another transition and we actually go into a shaded region, which means that again we don't know what that value is, it's indeterminate. And then it switches again and becomes valid once more, and we proceed. So these are the kinds of things which you may see on timing diagrams, which will hopefully help you to read them a little bit better. Now, let's talk about flip-flops. The flip-flop that we're using is going to be a rising edge D flip-flop, indicated as a DFF, D flip-flop. And the element, the way that it looks, is we have a box, we have an input D, an output Q, sometimes also a Q bar, which I'm not going to include, and a clock input. And what happens with this, we can draw a timing diagram for this. We have our clock, and the clock signal is just going to be 0, 1, 0, 1, 0, 1, and so on, just to have proper operation of this flip-flop. And the signal D is going to be the input, and basically D is going to get propagated to Q on the rising edge of the clock as long as we don't violate any constraints. So let's draw a potential signal D. It'll start off high and it'll go until, let's say, over here. Then it continues, rises again, and falls over here and stays low for the remainder. And let's then see what happens to the signal Q. Well, Q will start off undetermined. So it doesn't actually matter what Q is to start with, because we don't really know. So again, as I showed before, I'm going to start it off as just being shaded in. Now, it takes a little bit of time for the input D to propagate to the output Q, just because this is an actual circuit element and therefore there are finite delays. Things aren't instantaneous. Therefore, on the rising edge of the clock, since D is high, we know that the output Q should become high, but it doesn't become high instantaneously on the clock edge. So we can denote our clock edges, the rising clock edges, as such. It doesn't happen instantaneously, but a certain amount of time afterwards. So we know that it's going to become high, and it'll become high, let's say, over here. And this amount of time that it took for it to change from indeterminate to high, we're going to call TPCQ, which will stand for the propagation time from the clock edge to the Q output. There are some additional things to consider with flip-flops, and that is specifically a setup time and a hold time relative to the active clock edge, so the rising clock edge in this case. And what that is denoted by, it's going to be a period of time before the clock edge called the setup time, and a period of time after called the hold time, T sub h. So T sub s and T sub h. And what they say is that the input D must be stable, that is, it cannot change during either T sub s or T sub h. In other words, D has to not change for the entire setup time and the entire hold time. These are fixed quantities that are always present around the clock edge. So I'll draw those in over here. So we can see that this is a property of the flip-flop itself, and again, is a constraint that must be obeyed in order to get proper results. So we can see that D here was stable for the entire T sub s and T sub h, and therefore it gets propagated properly through the flip-flop, and Q becomes high after a given delay. Now D drops low, but the flip-flop doesn't change because we don't have a rising clock edge yet. And D stays low over here, and finally at this clock edge we're going to see this new input D, and after a propagation delay, Q is going to drop and remain low. So once again, the difference between here and here, that's going to be the TPCQ. Now this keeps going, and D becomes high, but it actually changes within the setup time, which is a problem. That means that after the propagation delay, now Q actually becomes indeterminate. What this says is that Q isn't some invalid third value, neither a 0 nor a 1. It is a 0 or a 1. It's just that we don't know what it is because we violated the setup constraint, and therefore we're not sure what Q is actually going to be. And Q is going to remain in this indeterminate state until it's corrected by a later proper input. So in this case, D stays low. So after propagation delay, we know that Q becomes low and becomes a valid value of low once again after a propagation delay through the flip-flop itself. Now let's take a look at something a little more complicated, a D flip-flop with some kind of a feedback path. So we're going to look at a D flip-flop with feedback, and we're going to make a simple feedback path to start. So we have our flip-flop, and the feedback path is going to go from Q through an inverter back to D. What we want to find in this case is the fastest clock that we can use to time this without getting any mistakes. So a mistake will happen if we get an indeterminate value of Q, for example, like we had over here because we violated a constraint. And therefore we don't want that to happen. So we need to look at all of the things that are going to cause a delay in the circuit and make sure that our clock period is longer than that. So the clock, again, its timing diagram is going to be something like this. And the clock period that we're talking about is going to be the time from one rising clock edge to the next. We'll call it T sub C, the period of the clock. So the things that are going to happen in this circuit is that we're going to have a delay going from D to Q, as we mentioned before. That's our TPCQ. And also, we're going to have a delay going through our combinational logic. So in this case, it's just a single inverter. And we want to know the maximum delay that we can incur over here. So we'll call it T propagation TP max. That's something that we can calculate or something that might be given to us. So what we're saying then is that the propagation time through the flip-flop and through the combinational logic must be less than some amount. Now, don't forget that there is also going to be a setup time inherent in the actual for the actual flip-flop, this T sub s. So therefore, we know that both of these delays plus the setup time must be less than the total clock period. In other words, at the rising clock edge, we start this propagation through the flip-flop, so that's going to be some propagation time over here, this TPCQ. After that, we're going to have to propagate through the combinational logic, so that's going to be another amount of time here, TP max. And then T sub s has to be held stable, right? We have to hold D stable for a duration of T sub s before the next rising clock edge. So as long as all three of these things fit within a clock period, everything is good. So this will be our good case. Now, we can imagine that there can be a bad case. Suppose that instead, during our clock period, our propagation through the circuit, through the flip-flop, that is, TPCQ, and then the propagation through the combinational logic will take, let's say, this long. TP max is rather long in this case, and our setup constraint is actually this long. So we can see that all three of these things do not fit within a given clock period. What this is saying is that D could potentially still change all the way up to this point, which would violate the setup constraint. So if everything goes in the worst case, if the propagation to the flip-flop takes this long, and then the time to propagate through the combinational logic takes its maximum value and it happens to be this long, then we're violating the setup constraint and Q is not going to be a proper value. So therefore, this case would be bad. And altogether, we can write down our constraint in the sense that we have that T sub c, the clock period, has to be greater than or equal to T PCQ plus T P max, the propagation to the combinational logic, plus T setup. If these three things can all fit within a clock period, then everything should be good. And this will tell us the minimum clock period we need to use in order to have safe circuit operation. If we look at this circuit closely, there is actually another constraint that must be maintained. And this is a hold time constraint. So this one is not quite so clear. What this basically says is that things cannot propagate through this circuit too quickly either, because that can overrun our previous input. In other words, suppose that this is our timing. So this is our clock signal. And then we have our D signal. And so remember that after the clock edge, there's going to be some kind of a hold time where D cannot change. And so suppose now that TPCQ, that starts right away after the clock edge, that goes on over here, TPCQ. And then we have our TP max, or in this case TP min, the minimum time that it can take to propagate through this combinational logic, because that's what we're going to be concerned with. And notice that this ends before the end of this hold period over here. And that's going to be a problem, because D now could potentially change. Let's say D started off as a 0, but after evaluating the combinational logic, it actually changes to a 1 at this point. And we can see that this, of course, violates the hold constraint because D changes within the hold time. And therefore, again, we're not going to get a proper propagation value for Q. So basically, our new output overran our previous input because we have this feedback loop. And that violates this hold time constraint. So this is, of course, a bad situation and imposes yet another constraint that basically says that TPCQ plus TP min, that is the minimum time it takes to propagate through the combinational logic, that best case, has to be greater than or equal to T hold in order, again, to not overrun our previous input. When analyzing flip-flops with feedback, it is often a good idea to actually redraw the diagram in a linear way instead of having this feedback. So we have our previous circuit over here with feedback, and it goes through an inverter and back to the input. Instead, we can redraw that as being a flip-flop to flip-flop path. So we have DQ and clock here for this flip-flop, and then we have an inverter, and that goes to a flip-flop. In this case, this flip-flop happens to be the same exact one. We're just redrawing it in a different way, but it makes things potentially easier to analyze because you can proceed in a linear fashion. So again, on a rising clock edge, we know that D starts to propagate through Q, and so we have this TPCQ, and then we have over here the propagation time through the combinational logic, which is going to be TP, and for analysis either max or min. And then we arrive at the next input, and we know that we have to maintain that setup constraint. So this will help us to analyze more complicated paths by drawing these flip-flop to flip-flop paths. Because in this case, again, it's easy since there is just one flip-flop, but in other cases it'll be more difficult when there are multiple flip-flops and multiple paths available. As an example, let's look at a feedback path that is a little more complicated. It's still going to be just a single flip-flop, but now its path is going to involve an inverter and also a NAND gate, which is going to be fed by an external input X as well. We can again linearize this, where we can trace through and see that this output is going through an inverter and then a NAND gate with the other input coming from this external input X, and this goes back to another flip-flop, which is actually the same flip-flop. And once again, we can perform the same kind of analysis where in a clock edge we go from here with TPCQ, and then we go through all of the combinational logic with our propagation delay over here, and we know that X is not going to delay us because X is immediately available. It's not being restricted by anything else. There's no delay that X produces. So therefore, we just consider this whole combinational logic block, and this brings us to the following input once again, where we again consider the setup time as before and proceed with a regular analysis. As a last example, let's look at something more complicated and go through how we would analyze it. Here we have multiple D flip-flops, 3 of them in this case, and I'm not drawing the individual clock signals, but each one of course is going to be clocked by the same clock, and each one goes through a feedback path with some combinational logic. So we have an OR gate and a NAND gate, NAND and AND, 2 NANDs and a NOR gate. Again, this logic may not make particular sense necessarily, but it's just to illustrate the idea. And we have 3 inputs A, B, and C that are also factoring into this. So now we want to analyze what is the fastest clock period that we can use here. That is the shortest clock period or the highest clock frequency. And that's going to depend on the longest path from a flip-flop to a flip-flop, taking into account both the propagation through the flip-flop itself and through the combinational logic that is going to be associated with going back to a particular input. And of course, the setup time constraint. So in order to do that, we need to find all of the flip-flop to flip-flop paths. If we look at the first flip-flop here, we can see that it has a path going back to itself through this combinational logic. So that path will look something like this, where we have our flip-flop, and then its output Q0 goes through an OR gate, and the other input to the OR gate is going to be the output of the second flip-flop, Q1, which we draw right here. It's coming in from the outside. And then it goes to a NAND gate where the second input is the input A. We see that again coming from the outside. And that goes back to D0, so it goes back to the same flip-flop itself. We have this flip-flop to flip-flop path. And again, the analysis is going to be exactly the same. We look at the propagation through the flip-flop, so TP-CQ, then through all of the logic, TP, in this case, if we're trying to find the minimum clock period, then it's going to be TP max. And we again back at the input here where we have to obey that setup time constraint. Q1 is not going to present any kinds of problems for us here because again, Q1, Q0, and Q2 are all going to be available at the same time after a rising clock edge, after a TP-CQ time. So after TP-CQ changes, assuming we're using identical flip-flops, Q1 should be ready. It should be a proper value from before, and therefore it's available immediately for this OR operation with Q0. And so we can look at other such paths. For example, if we look at Q0 again, or this first flip-flop, there's also a path to the second flip-flop. So it goes from Q0 into this NAND gate with B, and then into an AND gate with C, and into the second flip-flop. And so that path looks like this. Now, there are some other paths. So from the second flip-flop, from this one, we see that there's also a path to the first one, and it's going to be very analogous to the first one over here, where the input to the OR gate now is the output of the first flip-flop, Q0, and again we go back to the first flip-flop. And then there is another path going to the second flip-flop, to the third flip-flop from the second, which goes through here with these two NAND gates and the NOR gate and into here, and from the second flip-flop back to itself around that same similar path. And that's shown in these two paths over here. So again, you can trace through how we go from a flip-flop to another flip-flop or from a flip-flop to itself. And so here we've traced out these 5 flip-flop to flip-flop paths, and we can find the one that is the worst among them. So depending upon the delays to the various gates, we can find the worst propagation delay. And so we can write our constraint equation as T sub C has to be greater than or equal to, again assuming identical flip-flops, TP-CQ will be the same among them, plus, and here I'll say the maximum among the various maximum propagation delays. So let's say TP max sub I to indicate the ith propagation delay through a piece of combinational logic, and we'll take the max among all of those. And of course, we need T setup in there as well, which again I'm assuming is the same for all the flip-flops. So T sub C has to be greater than the worst possible path that is present among these 5. And then in addition, we have our hold constraint, so TP-CQ plus the minimum of the TP mins has to be greater than or equal to T hold, which again says that in the best case, the fastest possible propagation must not overrun our previous input, and therefore we have to obey that hold time constraint. Overall, we have seen how the various properties of a sequential circuit influence the clock frequency that we can use for the system. The setup and hold times of a flip-flop provide some rigid rules that must be obeyed around the clock edge in order for the flip-flop to function properly. Additionally, the intermediate combinational logic provides some constraints as well, since it also presents a propagation delay. Taking all of these factors into account, we can find the maximum clock frequency for a given sequential circuit topology.